In this video, we're going to look at a variety of different examples looking at applications of circular motion. In our previous video, we developed two equations that would calculate actually how fast an object is accelerating toward the center of a circle, and we call that the centripetal acceleration. Because when an object is going around a circle at a constant tangential velocity, it is accelerating even though its speed isn't changing. It's changing its direction, which is an acceleration. So we can calculate how fast it's accelerating by taking the tangential velocity and squaring it and dividing by the radius. And then if we knew the angular velocity, that's the Greek letter omega, we can calculate the centripetal acceleration. It is equal to the radius times the angular velocity squared. And then when we take Newton's second law, a lot of times it's acceleration is the sum of the forces divided by the mass, but we often see Newton's second law like this as well. One important thing to understand about Newton's second law is that the acceleration is going to be in the same direction as the net force. So if we have a force toward the center of a circle, we call it a centripetal force, it will be causing an acceleration toward the center of a circle. We call that a centripetal acceleration. And then if I just substitute this equation in for here, we get the centripetal force is mv squared over r. And if I substitute this equation in for here, we get the centripetal force is mr omega squared. All right, let me just pause there because we're going to now start to use these equations. I developed them in the previous video and looked at them conceptually, but now we're going to use these equations. One of the real challenges of circular motion is like, where do we begin in solving this problem? So we begin in the jungle. What? Well, of sorts. We're going to go on a hunt. And to do a circular motion problem, we've got to hunt for an equal sign. Do you see the equal sign in the jungle there? A little hidden, kind of blends in. Sometimes it's hard to see. But I'm joking around. But if you can find an equal sign, you're done with the problem. You're done with the physics. The rest of it is algebra. Let me show you what I mean. We did this problem in the last video where you go up and around in the roller coaster here and you don't fall out of your seat, and we had to calculate what was the minimum tangential velocity. Well, it was like, where do we begin? If you can identify that in this particular problem the acceleration, the centripetal acceleration, equals the acceleration of gravity, that's where you start. If you can say, hey, as this roller coaster is going around here, it is accelerating downward just as fast as gravity, so you're not going to accelerate away from your seat at all because your seat is accelerating into you as fast as you're trying to fall. So if you can identify the equal sign here, you're done with the problem. Now we can just plug numbers in. The centripetal acceleration is v squared over r, and we still have g. I'm not going to plug numbers into the equation just yet. Let's go ahead and solve it for what the question was. Well, we got to multiply both sides by r. We have v squared, so we have to square root both sides. This is our equation now. Now we can plug our numbers in. The radius was 6.85 meters. The acceleration of gravity was 9.8 meters per second squared. Multiply those, take the square root, you get 8.2 meters per second, which was about 18 miles per hour after you do dimensional analysis. Okay, so that was just a review of one of the problems we did in the last video. Here's a problem I encountered when I was making a swing for my children. And it was an ordinary swing. They had to wear a rock climbing harness, and we really swung them hard. So I had to calculate how much tension was going to be on that cable, and to make sure the cable wouldn't break, because if the cable broke, they would go flying over our home there, and nobody would be happy about that. So I did sit down and do this calculation here. Now I didn't use this kind of rope, I used the steel cable, but let's just say we go to a hardware store and we buy this 1/2 inch diameter rope, and we see right there that it's rated for 220 pounds, 100 kilograms. And remember, if you take mass times gravity, you would get force. So 100 kilograms is the same thing as 980 newtons. So this rope here can handle 980 newtons. And we're going to vigorously swing these kids back and forth. And when they reach the bottom of the swing here, they'll be going about 6.0 meters per second. And then the radius of that was 5.0 meters. What I wanted to do was to calculate what's the biggest kid I can put on this and still be safe. What's the mass? And so that, you put a really big kid there, the tension could be so much that the rope breaks. So we're going to draw a free body diagram. That's just identifying all the forces on that object as if it's a single point. Well, we certainly have the force of gravity. Gravity's pulling down. The force of gravity we say is F sub g. A lot of times we just say that's WT, abbreviating for weight. And that's just mass times gravity. That really is just an application of Newton's second law. Force equals mass times acceleration. Well, then we have the tension in the rope pulling up as well. So these are the two forces. We've got tension pulling up and gravity pulling down. If the tension was less than gravity, they'd be accelerating down. But because the tension is greater than the force of gravity, they're accelerating up, or they're accelerating toward the center of the circle. So just like we're going to do, we hunt for our equal sign, and it can be hard to see sometimes, but the free body diagram helps us. But if I can see that the centripetal force is going to equal the net force, the difference of those two forces is the amount of force that's being used to accelerate them into a circle. So if you can say, hey, there's my equal sign, the centripetal force is equal to the net force, then we're done. The physics is done, the rest is algebra. So from that first slide, we knew that mv squared over r is how we calculate the centripetal force, and the net force, we had tension up and gravity pulling down. That's our equation. Now we just have to solve it. You may be tempted to cancel out the m on both sides here. It doesn't work. You can't cancel it out because there has to be an m in every term. There's not an m in this term, so it doesn't cancel. So just be careful there. And which is good, because if m did cancel, then it would mean it didn't matter how big of a kid we put on there. But let's go ahead and try to solve for t. I'm going to add mg to both sides. And then I'm still trying to get, I did that so that I could get the masses on the same side. Now I can factor out the mass. There's a mass in each term there, and I can factor it out. And I'm trying to get mass by itself, so I'm going to divide both sides by all of that. So the mass is the tension divided by v squared over r plus the acceleration of gravity. Now that I got it solved down for m, now I can plug my numbers in. The maximum tension was 980 newtons. We have 6.0 meters per second squared. We're going to square it. The radius and the acceleration of gravity, we find that a 58 kilogram kid is as big as you can put on there. If you convert kilograms to pounds, there's 2.2 pounds in a kilogram. 127 pounds is all that we could put on there. And even though it's rated for 220 pounds, accelerating through there like that, that's force would produce a tension of 220 pounds. All right, just a little where we're going with this. I just want to show you how I came up with this number here. I won't be able to do it for you yet because we have to talk about conservation of energy. But if we swing this kid all the way back here on top of a ladder and let him go, if I know how high up that ladder they went, I'll be able to calculate how fast they're going down here. And again, we have to do conservation of energy first. All right, let's do this problem. This seems like a good circular motion problem. And you may be swinging around on these things and think, boy, I sure hope those cables don't break. How big of a person can we put in there and make sure that we're still safe? So Let's just see if my numbers here are reasonable. The radius of this thing is 10 meters. My classroom is about 10 meters wide, and that's reasonable maybe, 20 meters in diameter. We're going to put a 75 kilogram person there, about 155, 160 pounds. The angular velocity is going to be 1.5 radians per second. So remember, a little more than 6.28 radians in a full revolution. So it's going to take a little more than 4 seconds to go all the way around like that. And I want to go ahead and calculate the tension. Remember, we've got to hunt for an equal sign. And I don't know where to start. What equations do we use? Well, let's draw a free body diagram. So let's identify all the forces on this person here. Well, certainly we have the force of gravity acting on them. And then we have the tension in these cables pulling back like that. I still don't see an equal sign that I can come up with. But let's maybe go ahead and break that tension up into components. A force horizontal, and we're going to call that a centripetal force. That horizontal force is what's pulling them toward the center of the circle. And then a force up like this. Think back to equilibrium. This person is not going to be accelerating up or down, so the net force should be 0 up and down. So however hard gravity is pulling them down, this component should be the same. But they're not in equilibrium horizontally. They are accelerating into a circle. Now, I'm pretty sure we can calculate the centripetal force, and I can pretty sure calculate the force of gravity. Can we see our equal sign now? Maybe Pythagorean's theorem, that if I take that and square it and add it to that squared, that should equal that squared. So if I square root, there's my equal sign. So let's go ahead and calculate the centripetal force. It is an angular velocity, so we're going to use this equation. And so we have the mass, we have the radius, the angular velocity squared, and that's going to be how much force is pulling that 75 kilogram person into a circle. And then we can calculate what they weigh, the force of gravity. It's just their mass times the acceleration of gravity. So this mass and that acceleration of gravity, that's what they weigh. So now we're just going to do Pythagorean's theorem solved for t. The 1690 squared, 735 squared, square rooted, 1840 newtons would be the tension. And I have to clarify, that's the total amount of force pulling that person into a circle. It looks like there's at least 4 cables attached to that person. So if they distribute their weight evenly, the force on each cable would be 1/4 of that. All right, let's do another problem. You look at this picture and think, what is going on there? Well, this is an old-fashioned ride. You can tell from the picture. But and I've ridden a ride like this before. It's pretty fun. You go in this round room, and they start rotating the whole room. And then when you're stuck up against the wall like this, the bottom drops out from there. And you stick to the wall. You don't slide down. And the only thing that's preventing you from sliding down is friction. Friction between you and the wall. So again, we're hunting for that equal sign. But let's draw a free body diagram, and maybe we can find an equal sign. This person here has the force of gravity pulling down. And in order for them to not slide down, they have to have an equal amount of friction holding them up. And there's one more force that's acting on them, and that is a centripetal force, which is caused by the normal force. The wall pushing against them is pushing them toward the center of this circle, which is toward the center of the circle. It's a centripetal force, but because it's the wall pushing on them perpendicular to the wall, we also call it the normal force. So do you see our equal sign? The force of friction has to equal the force of gravity. That way they won't slide down. Well, now we're done with the physics. Now we have to do the algebra. We have to remember how to calculate the force of friction. It's the coefficient of static friction times the force normal. and it was just the absolute value of that. And then the force of gravity is just mass times gravity. All right, so I said earlier that the force, the wall pushing normal to the wall, perpendicular to the wall, is the centripetal force. So this normal force here can be calculated with mass times radius times angular velocity squared. That's how we calculate the centripetal force. Look at this. Do you see anything that cancels? The mass cancels, which means whatever we calculate for here, it's going to work for any person in here, regardless of their mass. It could be a little kid or a large person. It won't matter. They'll still stick to the wall, as long as the coefficient of friction was the same. And if they wore different clothes, the material against that wall would provide different coefficients of friction. Sometimes it wasn't enough and you would slide down. So we're trying to solve for this. Let's divide both sides by the coefficient of static friction, and then still trying to get that by itself, we'll square root. Now that we've got that all by itself, we divided by the coefficient of static friction and we divided by the radius. That's how those two ended up in the denominator there. But now that we've got the equation solved for what we want, now we can plug the numbers in. I gave you the radius, I gave you the coefficient of static friction, I gave you that the mass is equal to m, and I didn't highlight that earlier. The mass was equal to m. Often when that happens, it will cancel out and means mass doesn't matter. But if you don't know the mass, just call the mass m, and hopefully it will cancel out at some point. But it looks like if we turn this thing around at 2.3 radians per second, it will, these people will have enough friction to stand up against the wall there and not slide down. Hopefully you can see that that's going to take just a little under 3 seconds to go all the way around, because about 6.28 radians in a full cycle. All right, my next problem. So let's calculate how fast this motorcycle can go around the turn. What's the maximum speed they can go and not skid out? They have enough friction. We're hunting for that equal sign. Often we need to draw a free body diagram first. So gravity is pulling the motorcycle down. The ground is pushing the motorcycle up, so it's not accelerating up and down there. But there's one more force, and that's the force of friction pushing the motorcycle into a circle. If you were on ice, there would be a lot less friction, and you wouldn't get pushed into a circle. You would fly off tangent. So let's go ahead and see if we can find our equal sign there. You have to be careful here. It might be tempted to say that this is equal to that, and it is, but if this is mg, this is going to be mg, and it doesn't get us anywhere. So let's see if we can be a little bit more careful with our equal sign. Here it is. Our equal sign that we hunted for in the jungle, the centripetal force is equal to the frictional force. However much friction there was parallel to the surface, that's what was pushing them into a circle. Okay, so, and again I said the mass was m, and we're trying to figure out how fast we can travel around that turn. So the centripetal force is mv squared over r. The force of friction was the coefficient of static friction times the normal force. But here's where we had to remember that the normal force was equal to what they weigh. And what they weigh, the normal force, is just mass times gravity. Here's where we can see that mass cancels out. So I did not need to know the mass. It's on both sides, it will cancel. Trying to solve for v, I'm going to multiply both sides by r. Still trying to solve for v, I got to take the square root of both sides. Now that I got my equation solved for v, I can plug the numbers in. I know the coefficient of friction, I know gravity, I know the radius, and it looks like 42 meters per second is how fast the maximum they can go. Because remember that the force of friction is a maximum. It could be less, but it couldn't be more than that. And that was about 94 miles per hour. That's after we did dimensional analysis. converting meters into miles, and converting seconds into hours. All right, let's look at these two problems here. This is a test track and testing out new cars and stuff. But let's say we drive around this banked turn here pretty slowly. So I'm not going to do this with numbers. I do just want to show you how you would make a free body diagram with this. But we're going to drive around this slowly. Okay, so we have gravity pulling down, that's the weight. We have the normal force pushing back. And what other force? Well, probably friction between the tires and the ground, but what direction is friction going to be? It's always going to be parallel to the surface, but is it going to be up like this or is it going to be down like that? Well, if you're just parked there, it would be wanting to slide down, so friction is going to be holding it back. And if we drive fairly slow, friction will also be holding it down from sliding, holding it back from sliding down. That's our free body diagram. We're done. So now let's break the normal force up into a component, horizontal and vertical. Those two became that one. So that cancels out. This is going to have a component this way and that way. So that cancels out. So in the up and down direction, it should be in equilibrium. So those two forces up should be balanced by the weight down. But in the horizontal direction, it's not in equilibrium. We have this to the left and that to the right, and the one to the left was a little bit more. That's the centripetal force. That's what's pushing them into a circle. Let's do that again over here. Gravity's pulling down, normal force is this way. If they're going around crazy fast, they'll want to be trying to fly off tangent here, and friction is going to have to be holding them back from going up. So this time friction is parallel to the surface, but in this direction. So I break that up into components, horizontal and vertical. So those two became, or that one became those two. This one becomes these two. So that cancels out. In the up and down direction, it's in equilibrium, but in the horizontal direction, this force and this force add together to give you a really large centripetal force. And that's kind of more of a complicated free body diagram. Let's say we work for the highway department and we have to calculate a turn for an on-ramp onto the highway or something. But we want to be able to calculate what angle to bank this turn so that it could be iced over completely and no friction was necessary to keep them into the circle. So we're going to bank this turn, and even if it's iced over like this, the ground can still push against the car normal to the surface. But if you're going too slow and you try to go around that turn, you're going to slide downhill. And if you go too fast, you're going to fly off tangent, going up the banked turn. But if you go just right, gravity's pulling down, the force of gravity, and the road, even though it's iced over, the road can't push parallel to the road because there's ice, but it can push normal to the road, perpendicular to the surface. That's it. Those are my two forces that are acting on this car. Gravity pulling down and the normal force pushing back. We said that we don't want to rely on friction. We just want the normal force to have a component in and a component up. To be in equilibrium in the up and down direction, the force up has to equal the force down. But to get this car accelerating correctly, that's provided by a component of the normal force. So we're going to post the speed limit at 35 miles per hour. This angle here is going to equal that angle there. 35 miles per hour is the same thing as 16 meters per second. The radius of that turn is 75 meters. The mass of that car, we'll say, is m, and hopefully it cancels out somewhere. And we want to calculate what angle to make that. All right, do you see your equal sign? got to hunt for it a little bit. It wasn't obvious this time. It is true that this equals that, but if this is mg and that's mg, saying mg equals mg, that doesn't help much. But here it is. Just like we used Pythagorean's theorem before, the tangent of this angle equals opposite over adjacent. I can calculate that. I can calculate that. So I can find that equation because the tangent of that angle equals opposite over adjacent. Now that we got our equal sign, let's just plug things in. The centripetal force is mv squared over r. The force of gravity is mass times gravity. And I said the mass is equal to m, and that's because it cancels out right here. Which means when we calculate this angle, it's going to work for a motorcycle, it's going to work for a semi-truck, it's going to work for a Tesla. It's all going to work because it doesn't matter what mass it is. Trying to get this by itself, I need to take the inverse tangent of both sides, and then I went ahead and plugged the numbers in. That's the tangential velocity, that's the radius, and this is the acceleration of gravity. Looks like 19 degrees. Perfect banking angle. All right, that's done with the applications of circular motion, but just real quick, a little bonus thing from geometry. Let's say that we're going to go around this turn and we want to calculate how fast we can go and not crash, roll, flip, and burn. So we need to know the radius of that circle. So straight across there. But in the middle there's all sorts of trees and there's rocks and stuff, so you can't easily directly measure from here to there. That's where you have to come up with the intersecting chord theorem. If two chords intersect inside a circle, so that one is divided into segments of length A and B, and the other into segments C and D, then AB is equal to CD. Means that times that is going to equal that times that. I'm not proving that for you, but a geometry teacher should do that for you. And then this is just a special case of that. If this chord is the perpendicular bisector of that chord, meaning it's at a right angle there and it cut it into two equal parts, then it's still going to be true. That times that is going to equal that times that. Okay, I'm showing you this. Why am I showing you this? It's so we can measure the radius without having to go through that mess there. This times this is going to equal C times C. So let's measure A and let's measure C, and then we're going to calculate what B is. So B is just going to be C squared divided by A. So I measured A, I measured C, and then I figured out what B was from those measurements. Once I know what B is, I can add it to A, that's the diameter. The diameter divided by 2 is the radius. All right, so let's show you how we might do that. I could do all of my measurements right over here. I could just draw a line from here to there, measure the length of that line, divide it by 2 to find the midpoint, and then measure from that midpoint perpendicularly out to the rim, so I find A. So I now know C, I know C, I find A. So knowing C and A, I can calculate B. Knowing B, I add it to A to find the diameter, divide it by 2, I've got my radius. Now I can figure out how fast to go around that turn. That's all I have for centripetal acceleration and applications of circular motion.